hydrogen ion, anion. That's how you recognize an acid, right? And here I was talking about HCl. It dissociates completely because it's a strong acid. And you know all the strong acids, right? Because it was on that table I asked you to learn last semester. But it's also on the table I gave you earlier in this semester. So you want to know the strong acids, but we're not going to start talking about weak acids. Speaking of that, by the way, this does have an equilibrium. There's always going to be some of this and some of this. But the equilibrium constant here is about 10 to the 8th or 10 to the 9th. So if I started with 0.1 molar, and the equilibrium constant was 10 to the 9th, this would be 0.1, and this would be 0.00001 at least, or 9. In other words, depending on the K, because I don't remember exactly, I forget if it was 10 to the 8th or 10 to the 9th, but this would be minus x plus x, and x would be 0.0999999, something like that. So there is always, in any chemical reaction that you write, an equilibrium. But we don't talk about equilibrium constants for strong acids. We just assume they dissociate completely because the amount of undissociated acid is so small, unless we're carrying 12 significant figures or 10 significant figures in our answer. It doesn't make any difference. And we never, as I said, I'm happy when you do 3 significant figures, and so we don't have to worry about the 10th or 11th significant figure down the line. So when we're talking about strong acids, they dissociate completely. That's what I was just doing here for HCl example. Now I want to talk about a weak acid. In other words, it dissociates, but it doesn't dissociate completely. And the first person who discussed that weak acid was Arrhenius. You remember him, right? Reaction coordinates in the kinetics chapter. So Arrhenius was the first person to discuss this, and he said, we have to worry about the H-A, in other words, the hydrogen bond to whatever other anion you have there. The stronger the bond, the weaker the acid, i.e. less dissociation. And you remember, this is a dissociation reaction where you're breaking this bond apart. And that seemed pretty good. That's the first explanation of the weak acids and why things like HCl dissociate completely. Something like acetic acid did not dissociate completely. And so he said it depended on the bond strength. But one of the things that happened when people got fancy, instead of working in water, they worked in liquid ammonia. And acetic acid and liquid ammonia dissociates completely, just like HCl or any of the strong acids. And now the question is, why? Well, people have answered that. Two different people. Bronsted-Lowry theory says you have to take into account the solvent. The hydrogen ion goes from here to the solvent. So now there are 2 bond strengths to worry about. This bond strength compared to this one. If this bond strength stays constant and this bond strength gets stronger, the reaction goes more in that direction. Okay. So now we have to worry about both the solvent effect and the bond in the weak acid itself. And by the same token, we can talk about the corresponding mechanism between the hydrogen, the hydroxide ion, and the rest of the base when we're talking about bases. So I'll come back and do the bases. This is the general relationship. Now what happens here is we talk about conjugate acid-base pairs. This is just terminology you have to be familiar with. Okay? And in a conjugate acid-base pair, you have to have an acid partner and a base partner. The acid has the extra hydrogen ion. And different books will talk about pair A and pair B, pair 1, pair 2, etc. I'm going to use the pairs 1 and pairs 2 way of talking about it. But if you look at this thing and this, the only difference between them is an H+. If I take away an H+, it got more negative, and there's only the A part left, the anion. So this is pair 1. And this is still part of pair 1, base 1. Then these only differ by these square boxes. Again, this has one more H+ than this. So this is base of pair 2, acid of pair 2. In other words, there's two pairs in here. And what you now say is an acid plus a base gives you a new acid and a new base. And if this is a stronger acid, it wants to dissociate more. This dissociates, wants to dissociate more. This dissociates less, and it becomes weaker. So it depends on the relative acid-base strengths of these two partners. As this gets stronger, this gets weaker. As this gets weaker, this gets stronger. In other words, it wants to go more in that direction. And you could say the same thing about the base thing. So this is Bronsted-Lowry, and he talks about conjugate acid-base pairs. And this is the formalism we're going to use when we do acid-base equilibrium. If we do Arrhenius way of doing it, and when I went to school, that was mostly what they did in the textbooks, but they wanted to be a little bit fancier. As time went on, they didn't want to lead students astray, so they moved away from the Arrhenius theory to the Bronsted-Lowry. The third acid-base theory this is just a way of review to remind you about the three different acid-base theories. We already talked about Lewis acid-base theory when we were doing what? Complex ions, because the central metal behaved as a Lewis acid, the ligands behaved as Lewis bases. And so instead of talking about hydrogens at all, when we do Lewis acid-base theory, we talk about electrons. Lewis acid gains electrons, Lewis base loses, or they use the word donate electrons. So notice, here's my acid. It got more negative, so it gained an electron. Here's my base. What did it do? Well, it got more positive, must have lost an electron. Okay? So we can apply the Lewis acid-base theory to anything. Things without hydrogen ions we can apply it to. Okay? Whereas when we do this one and this one, we have to do hydrogen ions. Now, one of the reasons we got rid of Arrhenius, we always used to talk about this. And this is the base dissociation now. We made hydroxide ions. The big problem is, when we started looking at the solutions with ammonia that we called ammonium hydroxide, and the bottles still sometimes say ammonium hydroxide, you can't find very many of these molecules in there. You find mostly ammonia molecules and water molecules. Remember the other day I said, this is equivalent to NH4OH. And that's why all our bottles in the lab say NH3, aqueous. You want 15 molar ammonia? That's what you'll find. You want 15 molar ammonium hydroxide? You won't find it. But later on in the lab book, he's going to ask you to add ammonium hydroxide, and people always come running up to me and say, I can't find the ammonium hydroxide. I said, sure you can. Think about it. That's the bottle that says NH3, that's why. And also on that little sheet of paper, I think I called this to your attention in the lab, I listed all the acids and their concentrations and all the bases and their concentrations that we have out there on the reagent shelf. Okay, so you know what to look for. And when I listed ammonia, I put down sometimes called NH4OH. So you would be reminded of that. So now with that part of the experiment, you're tempted to run up and ask me. You can ask me, I'll still tell you the same thing, but I'll say remember. And everybody says, you keep saying remember. I expect you to remember every word I say until the end of the semester. Oh, no wonder. And things I didn't say to you, like things I said last semester. Okay, so this is the general setup. We're not going to use Lewis acid-base theory. We already mentioned it with respect to complex ions. We're going to forget about Arrhenius. He started things off. And we're going to work with Bronsted-Lowry. Okay. Notice I want to use Bronsted-Lowry here for HCl.